Hi, physics class. Okay, we're moving on to lesson 2 of Unit 1, Energy Conservation, Renewable Energy. This is on Coulombs Law. This is the hardest lesson in the entire course. They give you a very long problem, which I have worked for you on a video. And my advice to you is, unless you really want to learn that, I would skip it. As I say, it's on a video. It requires you have a good knowledge of trigonometry. I've done a different video to be sure you have that knowledge of trigonometry, and it also requires you understand vectors pretty well, and I've done another video on that. So all those videos are available in this lesson in Google Classroom, and they're also under all videos. I always put videos under all videos in case you don't remember where a particular video was. All right, one other thing I'm going to show you that I did put in all the lessons in Google Classroom is a formula sheet. I think it's pretty complete. But it basically has the formulas you're going to need both for the previous lesson, electrostatics, and for this one in Coulombs Law. Down below, by the way, is a table so you can understand some of the symbols that are used. The one you see quite a bit in these lessons is this one. It's micro. That's the letter mu, Greek letter mu, mu. It means micro, and it just means 10 to the minus 6th power. So it's 1/1,000,000th of something. So, but all the others, and you really almost don't see any of these others. You'll probably see kilo or milli or centi along the way somewhere. But anyway, so if you need to know what those symbols stand for, there they are. Okay, let's go ahead and get started on this. So in the last lesson, Coulomb's law is an equation that gives a force between two electrical charges. So we dealt with this equation already in electrostatics. Lesson 1, Fe, the force, electrical force, that's what that means. F subscript E equals charge times electric field. You could think of it kind of like your weight. Weight is a force. And it's the force that the mass of your body, when the mass of your body interacts with the gravitational field, it gives you a force that we call your weight. This is exactly the same thing. All these forces work the same way, even though they seem totally different. So the electrical force is equal to the charge. That's comparable to your mass in a gravitational field. It's the amount of charge you have times the strength of the electric field, and that's comparable to the gravitational field. All right, so they give you this is a warm-up, so it's basically going back and doing some of the things from the previous lesson. So this is under the warm-ups in Coulomb's Law, square number 3. The squares are the ones down at the bottom of each lesson where you move from one square to the next through the lesson. All right, so a charge of 9.0 times 10 to the minus 5 coulombs is placed in an electric field with a strength of 4.0 times 10 to the 4th newtons per coulomb. That's the unit of measure for an electric field. What is the electrical force acting on the charge? So you simply multiply those two numbers, and if you weren't sure whether you should multiply them or not, right here, if you know that force is in newtons, then you know that the c's have to cancel out. So you have a c there, and you have a c down in the denominator there. So you can cancel units the same way that you cancel that you cancel variables in algebra class or numbers in math. So those cancel. So what you end up with is newtons, and that's what's in the final answer. So that's a method you use particularly in chemistry class when you get to chemistry. So again, the method for doing scientific notation is you take the coefficients and you multiply them, and then you take the exponents and you add them. So 9 times 4 is 36, and negative 5 plus positive 4 is negative 1. So that's what you get. But to write scientific notation properly, you should move the decimal over so it creates a number between 1 and 10. Again, if you haven't watched the scientific notation video that I did, it's about 17 minutes long. Go watch that because you're going to be using scientific notation throughout this class. So you want this to be a number between 1 and 10. So you move the decimal over between 3 and 6. So that's 3.6. That's a number between 1 and 10. So there it is right there. Okay, because you move this decimal over one place to the left, since you made this number smaller, you went from 36 to 3.6, you have to make this number bigger. And bigger means you go in the positive direction. So you'd be going from negative 1 to 0. That's bigger. So you end up with 3.6. This number is smaller than that, times 10 to the 0. This number is bigger than that. So these two numbers are exactly the same value. Now 10 to the 0 power, any number to the 0 power is 1. So 1 times 3.6 is 3.6, and that's the final answer. As I've said before, I believe in the earlier video, they they do something that you usually don't do. If you start with a problem in scientific notation, you usually end with it in scientific notation. But they don't. They usually have you convert it to a regular non-scientific notation number. So be prepared to do that. That's all in the scientific notation video, how to do that. All right, let's move on. Okay, so Coulomb's instruction squared number 2. So we're now to the instruction part of the lesson, no longer in the warm-up section. Square number 1 was just kind of an introductory blurb, about 30-40 seconds. So I skip those. I just go to the ones that are things that you really need to know. So the inverse square law means that the force between two charges is inversely proportional to the distance between them. And I really should have said inversely proportional to the square of the distance between them. So you can add that word in. The square of the distance between them. So what does that mean? Inverse means that if one side of the equation is in the numerator, is on top, the other side is on the bottom. So as this gets bigger, this is going to get smaller. As this gets smaller, this is going to get bigger. They move in opposite directions because one is up on in the numerator on one side, and the other's in the denominator in the other. And then it's not just the distance, but the distance squared, as I added right there. So the way you do this is you just pick some numbers to use to play around with and see how this works. So let's test it out. So the force is proportional or equal to the inverse of the distance squared. So let's say we start with a distance of 1. So we plug a 1 in for d. So 1 over 1 squared equals 1 over 1 equals 1. Okay, so that's our initial distance. Now, what if we doubled the distance? We change the distance to 2. Then you have 1 over 2 squared equals 1/4. So what happened? When you doubled the distance, you increased it by 2 times, the force became only 1/4 as strong. They use the phrase decreased by a factor of 4. I don't like that because it's not clear what that's really saying. I like to say it became only 1/4 as strong as it was before. So doubling the distance weakens the strength of the force to 1/4 what it was before. All right, let's look at another example. This one. So we start with 1 over d squared. If d equals 2, then 1 over 2 squared equals 1/4. Same thing we have up there. Now we're going to see if we cut the distance in half. So we're going to go from 2 right here down to 1 right here. We're going to cut the distance in half. So how does that affect the force? Well, if we do that, put a 1 there, then we have 1 over 1 squared equals 1. So what happened? It went from 1/4 to 1. So by cutting the distance in half, the force became 4 times stronger. 1 is 4 times 1/4. So logically, just think of it logically first of all. When you bring two objects that are exerting a force on each other together, they're going to exert more of a force on each other. When you move them farther apart, they're going to exert less of a force. You feel the gravitational force of the Earth, but if you went a billion miles into outer space, you would no longer feel the gravitational force of the Earth. So that's what they're saying. So first of all, just kind of think about, okay, they're getting closer. Is the force going to get stronger or weaker? It's going to get stronger. If I move them apart, is the force going to get stronger or weaker? It's going to get weaker. And then this is how you do. Again, just pick a couple of numbers to work with, distances, and see how they affect it by making that change. Okay, we're going to move on to square 3 in the instruction section of the Coulombs Law lesson. So this is the problem they gave you. I made up those on the last page. So if the distance between two charged particles is increased by 4, so it's 4 times greater, the force will decrease by what factor? Again, they use that phrase, decrease by what factor. So again, just pick some numbers. We start off with d equals 1. There's the same equation you saw before, so that equals 1. If you increase that by 4 times, then that becomes 1 over 4 squared is 1/16. So the distance is increased by 4 times. The force will only be 1/16 as strong as it was before. So much, much weaker than it was before. All right. We move on to square 4. So Coulomb's Law is the main topic of this lesson, and this is Coulomb's Law. And what it says is the electrical force is equal, let's just read this. In words, it says that the force between two electrical charges, Fe, electrical force, is equal to the magnitude, that's the amount of the two charges, Q1 and Q2, times Coulomb's constant K. So this is then divided by the distance between the two charges, which is d squared. So there's that inverse square relationship, and that's why they wanted you to understand that. So the Coulomb's constant was determined from experiments to be this number right here. Okay, and sometimes students look at this and they say, what does that mean? What's all that? That's kind of a mess. And here's what it does. What it does is it makes the units of measure cancel so that the units of measure in the final answer are correct. So in the equation above, if you have a value for Q1, Q2, and D, and you plug those in, you want to end up with force in newtons, so it makes all of the other units of coulombs, and meters squared, because that's distance squared, it makes all of those cancel out so that the only unit you have left in the final answer is newtons, which is the appropriate unit for force. What if you knew force and you knew the two charges and you wanted to solve for the distance? So if you're given force, Q1, Q2, and are solving for the distance d, then the units of measure will cancel so that you end up with meters, which is the correct units of measure for distance. You measure distance in meters. So it'll make everything cancel out appropriately so that you end up with the unit that you wanted to have at the end of the problem. Okay, so square 4, they're going to actually work a problem. Now this problem you should know how to work, and it's really just plugging in numbers. This is not the big complex problem I was talking about. Alright, so the first thing we are going to do is read it, and it says a positive charge, Q1, of 5 microcoulombs is on the x-axis. So let's slow down here. What's microcoulombs? So I showed you the formula sheet at the beginning. If you didn't know that, you come over here. There's the symbol, mu, it's micro. It's 10 to the minus 6. So that means you turn that into a scientific notation number of 5 times 10 to the minus 6. It says a negative charge, Q2, of 7 microcoulombs, same thing, negative 7 times 10 to the negative 6th, is 0.8 meters away. Find the force and direction. And although this looks complicated, it's really just plugging in the numbers. So there's a diagram of the situation. There's the two charges. They're oppositely charged, and they're 0.8 meters apart. And so let's read this. The symbol mu is micro, which is 10 to the minus 6th. I have included a list of what symbols like that mean on the formula sheet. We just saw that. So here's the formula. You just plug in the numbers. So there's K, Coulomb's constant. There's charge 1, Q1. There's charge 2, Q2. Don't forget the negative sign. And there's the distance, and then you square it. Okay, so now, this is the tricky part for some of you. How do you solve this thing? Well, you multiply all the coefficients first. So you take this times this. Whoops, I went too far. Times that. And then you multiply times that. So it's 8.99 times 5 times negative 7. Now, what about this thing down here? This is not in scientific notation. It's really just a number. And you can punch it into your calculator as 0.8 and then hit the x squared button or square button, whatever you have on your calculator, and that'll give you this number. So the way you would write this is right here. Now multiply 8.99 times 5 times negative 7 and divide by 0.8 squared. If you're not real good with your calculator, I would do that and write these down. Kind of do the top ones first, write them down, and then do the 0.8 squared, write that down, and then divide the top ones by the whatever you got for the 0.8 squared. Do it one step at a time and write them down. If you're good with a calculator, you can just punch all this in, in one time. But don't try that at first, because you're going to make a mistake if you're not really good with your order of operations and your skills on that. So anyway, you multiply all these together. And what you get is negative 491.6. That's down here. And now for the exponents, you add 9. 9 minus 6 is 3. Minus 6 again is negative 3. So there you go right there. That's that. Remember, this is not scientific notation. You don't include that in that calculation, that second part of the calculation. That's just a regular number right there. It equals 0.64, and that's what that is. That goes with the coefficients. Okay, so you got this, negative 491.6 times 10 to the minus 3. Again, watch the video on scientific notation in all videos if you don't know how to do this. And so now you have to make the coefficient a number between 1 and 10, or really in this case between -1 and -10. When you're doing this, forget about the negative sign. In other words, just make this a number between 1 and 10. To do that, you'd have to move the decimal right there between the 4 and the 9, so it would be 4.916. Okay, and I show that down there. Okay, I don't really mean forget the negative sign. I just, it's just you're focused on this, the number itself. Now, if you do forget the negative sign, though, and you move the decimal over here 2 places, you made this number smaller. It went from 491.6 to 4.916. That means you need to make the exponent bigger by 2 positions. 2 bigger than -3. What is it? Is it -5 or is it -1? Which way do you go? If you want to make it bigger, you go in the positive direction. So it goes from -3 to -1 right there. So this is the answer that you get right there. If you want to leave it in scientific notation, that's your final answer. But if they want it as a regular non-scientific notation number, then what you do is you get rid of this. You move the decimal over 1 more position to 0.4916, and this becomes 10 to the 0, which is 1. And 1 times that is that. There you see it right there. So the answer that they get, and the correct answer is -0.49 newtons. Okay, so again, the scientific notation might be the hardest part for some of you, but just keep practicing it. It will come through to you. Okay, all right, and we're going to move down, and they give you another one. Here's another one of the same type. So particle Q1 has a positive 6 microcoulomb charge. Particle Q2 has a positive 2 microcoulomb charge. Both are positive this time, so they're going to repel. The charges up here are attracted because they were opposite. These are going to repel. They are located 0.1 meters apart. What is the force? Same question. So see if you can set up that equation. I'm going to turn the page here in just a second. See if you can set that equation up for yourself, and then I will do it for you here in a second. All right, and this is what you should have gotten. There's Coulomb's constant. That number never changes. There's the 6 microcoulombs. That means 6 times 10 to the -6th. And 2 microcoulombs, there's 2 times 10 to the -6th. The distance was 0.1 meters, and you have to square that. So you do it exactly the same way. Multiply 8.99 times 6 times 2, and then divide it by 0.1 squared. And that right there will give you 10,788. Again, note that the 0.1 squared is not in scientific notation, so you group it with the coefficients. All right, 10,788. The exponents add up to exactly the same way they did on the last problem. 9 minus 6 is 3, and 3 minus 6 is -3. There it is right there. So you end up with 10,788 times 10 to the -3rd. And again, we're going to go straight to, this time, to converting it to a non-scientific notation number, since that's what they like to do. So again, watch the scientific notation video. So what do? The decimal's right here behind this 8. You don't see it there, but it's there. And so you move it 1, 2, 3 places to the left. The -3 means you're going to make it a smaller number. So that means you end up with 10.788. And there it is right there, 10.788. The video shows 10.8, same thing. All right. Again, go back and review these. Remember, this is a video. You can go back and review this if you don't understand something. If I'm going too fast, listen to it a second time. And then if you still don't understand it, that's what you want to do, is write down, I didn't understand this part of it. And when you come to tutoring, have specific questions. To just come to tutoring and say, I don't get it, is not helpful to me. I don't know what you don't get. You really want to learn to identify what it is you don't get. And I know for some of you it's the scientific notation. Okay. All right, superposition principle. Now this is one you should learn. This is part of that big complex problem, but it's just a fairly basic part of it. And you will learn this on the vectors video that I did, and how to add 2 vectors using the parallelogram method. So let's go ahead and read this. The superposition principle says that 2 component vectors can be combined to create a resultant vector. So in this case, these 2 vectors, this vector comes from this charge pushing this in this direction. And this vector comes from this charge pushing this charge in this direction. And I'll just do this kind of quickly and fast and easy here. If I take this one and measure it, and I get that that's about a 1/2 inch, and I slide it over here, or actually I'm going to make a parallelogram, right? So let me go over here. I'm going to slide it over here, yeah. And what I'm going to do, I'm showing you the parallelogram method. I make a parallelogram with a dashed line, and then this connects down to this tip down here. This vector right here is not there yet. You got to pretend like that's not there. That's what we're trying to find. Okay, that's what you would end up with. So the vector should really go up here. Oh, I'm sorry. They show this as the resultant, but that's not really a good representation. It would go from the tails here to across the diagonal of that parallelogram to right there. And you're going to see when you see the long problem, even though you're going to ignore it, that vector really kind of angles up a little bit like that. So in other words, when you add this vector and this vector, you get a resultant called this. These two are called component vectors, and the one that you produce from those two component vectors is called the resultant vector. That's why they give it an R. But again, it's not that. That's really the x-axis. It's really this. Okay? Again, watch that video, as I had said before. Okay. Combined pre-result. When A and B are added together using the parallelogram method, they produce a resultant vector R. Vector addition by parallelogram method is explained in my Google Classroom site. Go to all videos and watch the first 15 minutes of the vectors video. So that's about the 5th time you've heard that. Go see that video. Okay, important note. Squares 6 through 12 of this lesson, of the instruction part of the Coulombs Law lesson, present a very complicated problem. I explained this problem in the electrostatics instruction video found in the Coulombs Law lesson in my Google Classroom. You do not need to know how to solve this problem. Yes, on the unit exam they give you one question where you have to solve a problem like that. It's not worth your time. It's one question out of 25. Ignore it. Just guess. You got a 1 out of 4 chance of getting it right, which is probably better than your chances if you actually tried to solve it, because there's so many opportunities to make mistakes. If you watch my video, I made a couple of mistakes, and I had to go back and correct them. Ignore that problem, just move on. But the superposition principle you should understand. If they give you two vectors, what would be the resultant? Hopefully you can do that. That's not that complicated. There is one question on the unit exam out of 25 questions, and it is not worth your time unless you are highly motivated to learn it. The only thing you need to understand is the superposition principle shown here. Okay, so there you go. Okay, so we're going to continue on. Again, if you want to see the long problem, go to, there's a separate video on that in this same lesson, Coulombs Law. Okay, what they conclude this instruction part with is comparing Coulombs Law to the gravitational force equation. And you can see they look almost identical. The electrical force equals Coulomb's constant times the two charges times divided by the distance squared. For the force of gravity, it's the universal gravitational constant times the two masses. Now you can use this formula to compute your weight in newtons, and then weight in newtons can easily be converted to pounds. You can calculate your weight. One of the masses would be your mass. You would need to know your mass. The other one would be the mass of the Earth. And if you multiply it, which is, humongous, obviously, that's a major, major number. Okay, so there it is. Your mass times the mass of the Earth divided by the distance squared. Now that one's a little tricky. If you were going to compute your mass, how far are you from the Earth? What's the distance between you and the Earth? And your first instinct might be to say, well, 0, I'm on the Earth. But it's not from the surface of the Earth, it's from the center of the Earth. And that's about, I'm going to say about 5 million meters away. So that's what you would have to square, is that distance, 5 million meters squared, okay? But the point is, I just want you to understand what this can be used for. You can calculate your weight using mass. So these two are pretty much identical. Why are they so similar? Because they're both dealing with forces, and forces between two objects always behave the same way. So just because one's electrical and one's gravitational doesn't mean they're going to be totally different from each other. They are going to be the same. So Coulomb's law uses electrical charges and Coulomb's constant to find the electrical force. Gravitational force uses the mass of objects in a gravitational field and the universal gravitational constant G to find gravitational force. One difference, electrical force can attract or repel, that is push or pull, an electrical charge. Gravitational force can only attract, that is pull. Both of these forces have infinite reach. That's okay, theoretically, but not practically. You get farther enough from the Earth, you're not going to feel its reach. Now, they ask you in the video, compare the constants, and here's what's notable. This one is 10 to the 9th. That's times a billion. This one is 10 to the minus 11th. That's like 1/100 billionth. It's really tiny. This one's really tiny, and this one's pretty darn big. So what does that tell you just intuitively? It tells you that the electrical force is much stronger than the gravitational force. So Coulomb's constant K is much larger than the gravitational constant G, 10 to the 9th compared to 10 to the minus 11th. This means that the strength of the electrical force is much stronger than gravitational force. The reason we feel a strong attraction to the Earth is because the Earth is so massive. So the mass of the Earth in this equation up here is going to overwhelm that G number, and it's going to give you a fairly substantial force, namely your weight. All right, so here's a problem. They do an interesting problem. In the video, they ask you to compute both the gravitational and electrical force between two electrons and compare the strength of those forces. So compare the magnitude of the electromagnetic and gravitational force between two electrons separated by a distance of 2 meters. Assume the electrons have a mass, so you need to know the mass of an electron, and there it is. It's really tiny, 10 to the minus 31 kilograms. Tiny, tiny, tiny. And a charge of 1.61 times 10 to the minus 19th coulomb. So that's the number of coulombs on a single electron. And round to 2 decimal places. Okay, so what you're going to do is you're going to take the electrical formula, the Coulomb's formula, there it is, and you're going to plug in Coulomb's constant and the electric charge on an electron, which is the same, so these two numbers are going to be the same. And there's the 2 meters that they're separated by. You square that, and what you get is the electrical force is 5.83 times 10 to the minus 29th newtons. Now that's pretty weak. It's not a lot of newtons. Okay, you wouldn't even feel that. But let's do it for the gravitational force. So there's the equation for gravitational force. There's the gravitational constant up there. And then you multiply it by the mass, not the charge, but the mass of the electrons, which is the same in both cases. And you divide that also by the 2 meters squared, and you end up with the force of gravity between those two electrons is 1.38 times 10 to the negative 71st. So this one, forget about the coefficients. Look at the exponents. 10 to the minus 29th, which is small, but 10 to the minus 71st is just unbelievably small. Just really, really, really small. Much smaller than this. So the bottom line is, if you made a ratio of these two numbers to see how much bigger this one is than this one, this makes the electrical force, this number, I don't even know what that number is called. It's so big a number, I don't even know what it's called. That number times stronger than the gravitational force. So that's kind of an amazing fact of how much stronger electrical force is than gravity. Okay, this mercifully ends the Coulomb's Law lesson. Again, just understand the concepts, understand this, how to apply this formula to two charges, not three, forget that, and understand the vector concepts, and you'll be good for the Coulomb's Law. All right, we'll see you on the next video.